table of contents, probably we are talking, first of all, we're talking here about Eurocode in 1990, part 1. There are two parts. Part 1 is about new structures, part 2 is about assessment of existing structures. And that's, we're talking here about the first part, which is new structures. Main text, the normal openings, chapters 0 to 3, then the general rules, limit state design, the variables, structural analysis, and design testing, and verification by partial factor method. And also, there are lots of annexes. First of all, there are application annexes. That's the number A, and A1 is about buildings, A2 is about bridges, and there's towers and silos, structures supported by cranes, and coastal structures. Especially the last one is a bit of, it's not completely done yet. B, Annex B, measures for design and execution. I will come because there are quality issues which are related to E1997. C, reliability analysis, code calibration is how you can derive your own partial factors based on probability for your structure, so that it's connected to probabilistic design. Design assisted by testing, I come on that. Robustness, and then Annex X, I think there are more annexes. Annex X is on numerical methods. Consequence classes. I think this table has been shown before. We have the classes CC0 up to CC4, the highest consequence. Description is a bit poor. I think loss of human life, extreme, high, medium, low, and very low, and economic consequences huge to small. And then there are some examples in the buildings. A1, it's a nuclear power plant and a dam. 3, they talk about concert halls, stadiums, or where lots of people are together. Agricultural and storage warehouses are in CC1. And then there's something called other elements and structural. So these are the things which do not directly support something. They will be in CC0, and CC2 will be not covered in the other ones. So, and then for the bridges, there is a subclassification of CC3. So there's the big ones, they call it project dependent, and the railway bridges and bridges for major roads, they're also in CC3, but a CC3A, which is a bit lower. So the provisions in Eurocodes cover design rules for CC1 to CC3, so there's no rules on CC0 or CC4, but they say, well, yeah, you can also apply CC, do not entirely cover design rules needed for CC4. So you may use them, but it's not exactly to the level of safety for CC4. And of course, in 1997, we have our own differentiation in CC classes for geotechnical structures. The probabilities, there's two different betas are given. So we have the old betas for a 50 years reference period, which is the 4.3, 3.8, and 3.3 for classes C1, C2, and C3. Timo has already talked about these probabilities. And of course, if you need a probability, a 1-year probability, if you want to go to different reference periods, and so you can can calculate with that, you need this figure for a 1 year reference period. One of the conclusions was from the reliability study SC10 did, to forget about these 50 years probabilities and go for 1 year probabilities. However, we are used to these numbers, so they still kept in. Connected to it is the chances of occurrence. So it's 1 in 10 minus 5, etc. Robustness. Robustness is actually, it has been described, it is mainly that the definition is that it should not, the structure should not be damaged by an unforeseen adverse events to an extent disproportionate. And that means that a collapse of one beam should not cause the complete structure to fail. So it's against progressive collapse. And in geotechnics, you should think about a retaining wall with anchors, and if one anchor is failing, the whole wall is failing because the others are also losing their strength. Well, there's in Annex E on robustness, there are some design methods. What you can do, you can use prescriptive design rules to improve the integrity of the and the ductility of the structure. If you provide alternative load paths, normally in the Netherlands we talk about a second bearing draagweg, a second bearing structure, that when the first one fails of a huge building, that the second one holds the building up. The other thing is design structural members as key elements, and also segmentation, putting the structure in parts which stand on its own is a possibility. And for 3, you have to do extra things. You look at propagation of failures, better looking at risks. But it's very, the whole, it's very much not very specific, these requirements, unfortunately. Design service life. Design service life is specified in Eurocode EN 1990. They have monumental buildings, I think is 100 years, and normal buildings are 50 years. We have our own, made in Eurocode 7, our own service life, design service life for geotechnical structures, and that fits in the EN 1990 philosophy. Durability. Then we talk about deterioration of design service life. It should not impair the strength of the structure. And then we talk actually about corrosion of steel, corrosion of wire meshes, geosynthetics, when we're going to look into geotechnics. Also, I think it's fairly abstract. These are the measures they provide. I think it's fairly, of course, it's a checklist of things you should take into account. What is important is that there is in the bridges annex 2.5. I think that's very good. If you have structural parts which rely on the assumption of, in case of durability, it should have the possibility to inspect or be to have maintenance of the structure to check whether the durability of the structure is at stake. Of course, there's a second clause: when you can't do it, then you have to design your structure that the durability is guaranteed without inspection during its lifetime. But inspection and maintenance, I think it's an important issue in case of durability. Sustainability, another key word in EN 1990. It is defined as that the structure should be designed to limit its impact on non-renewable environmental resources, or on society, or on economy, and some potential strategies have been given there, and but we have taken that on in EN 97 in part 1 in the strategies for geotechnical structures. So we already did something. We took already these things into account for geotechnics. Quality management. The idea of 4.8 is to have organizational procedures and controls to guarantee the structure to correspond to its requirements and assumptions. So it should be designed correctly and executed correctly, but then it should be controlled and the organization should be okay. So why is it important? I think because it is difficult. Our models are getting more and more complex, so I think it's difficult to check. Much data. We get more and more data. The number of CPTs, the number of lab tests is enormous. That may be that lead also to complex ground and design models. So we need a thorough checks. And the other check we must do always, can we build it? We got also some quality management tools in Eurocode 7, and they're partly based on Eurocode EN 1990, and we coupled them to the geotechnical categories. And they are these rules. We refer there to EN 1990. They comprise design quality, design checking, execution quality, and inspection during execution. So design quality is dealing with the qualifications and the experience levels what an engineer or a designer would need. In that annex, which is informative, B gives in table B1 is the different levels for designer, and so it's complex. It's abstract. So you should have qualification and experience to do a complex design, an advanced design, or a simple design. But and it can be completely filled in the National Annex, but it gives a possibility for setting requirements to the designer. This is a bit, I think, in discussion in Europe. I think some countries would like to follow this, others don't, but the option is there, and we also connected it to the geotechnical category, as you see in the first column. Now the same for design checking, and that's the idea is to reduce human errors, to check the design. For GC3, we would then say extended independent checking, and then I think on a third party. GC2, it says normal independent checking, I think within the company, a colleague, and GC1 is self-checking is enough. But really, these are things, they are done nationally, so the NDPs, and can be used in the National Annex of Eurocode EN 1997 Part 1. Now here's some the things you could check, but it's really straightforward. Execution quality. So there is an urge to check the execution and execution quality together with the geotechnical execution standards. For instance, where Karsten Beckhouse talked about, these standards should be looked at. And the last one is inspection during execution. Also here are inspection levels defined in EN 1990, which are coupled in EN 1997 to the geotechnical categories. Again, NDPs, so countries can decide whether to follow these. And then, there is the last paragraph of this chapter. This annex is it should be according to the consequence of failure. So and special for the geotechnical structures is a reference made to EN 1997 Part 1. So it is, and also as geotechnical category, so the consequences of failure and the complexity of the ground dimension. Limit state design, nothing new. We talk about design situations, persistent, transient, accidental, seismic and fatigue. General principles about ultimate limit state and serviceable limit state. And then we come to the actions, basic variables, variable actions. Here the definitions are given for the various actions. The characteristic value, QK, and that's actually the leading variable action. A combination value is a second variable action together with the leading one. Well, we call that the combination value, and that's a factor psi, a reduction factor, times the characteristic value. A frequent value, which is used in accidental limit state or a reversible serviceability limit state, multiplied by psi1, and a quasi-permanent value connected with psi2. And then characteristic value is an upper value or a lower value, and if it's not known, a nominal value. And also the probability. Water actions, I can be short. In EN 1997 we have rules for groundwater, and there also we follow this, a single characteristic value with a mean value, or the owners of an upper and lower values as permanent actions. And water actions are classified as variable. Then you can take a mean representative with a variable component, and and then the representative of that variable should be again with a characteristic, frequent, quasi-permanent, or a combination value. Actually, and also there's some, if there's a physical limitation, then you can take a nominal action. Well, the whole thing is actually conform EN 1997, or EN 1997 is conform EN 1990. Material properties, again, the general issues I think were already highlighted in the lecture by Jose, the 5% fraction and the 95% fraction to determine a characteristic value. I think it's all written down, but I think we took that on in 1997. There's also an Annex D to determine the material properties based on statistics. I think we got a similar and better one in EN 1997, Annex A. Structural analysis in 7.2. Non-linear analysis should be used when the behavior has a significant influence on the forces, which is often in geotechnics. I think non-linear numerical methods should be validated. A sensitivity study should be carried out. I think those things are really, logical, and we have taken that on in 1997. Partial factor methods. Here the famous equation ED is smaller than RD, the load is smaller than the resistance, but important to note is that also the ULS for excessive deformation has been taken in 1990. A combination of actions. I think people who use the old version, there's a formula 6.10, which is now translated to 8.12. It's actually the same formula. It's the sum of the actions is a permanent action times a action factor plus the biggest variable action times a factor, load factor, and the rest is reduced by psi. So they're combination variable combination actions. And then there's we had the alternative. This was the general formula. We had an alternative where you put take into account the complete permanent action and a reduction on the first variable action, and or reduce the permanent action by a factor psi and take the complete variable action into account. Nothing new. The only thing is there's two new formulae added on a few countries who used this kind of formulation. Accidental actions, again, in this case you have the design action, the design accidental action combined with characteristics values of the permanent actions and of the variable actions, and even reduced by a reduction factor. So if you do an accidental, it's only the design value of the accidental action. And the same applies for seismic actions, but I think Sebastiano will talk about that as well. Partial factors for buildings. I think you have seen this table already a few times these 2 days. I only wanted to say here you have the one for foundations, VC1, the uplift values, VC2 for uplift and ACU, and then the two geotechnical cases, VC3 and VC4. What is important, we had originally in Eurocode 7 the serviceability criteria. Those have disappeared, but in 1990 there is a table with serviceability criteria, which are maximum differential displacements. So as shown in the top, delta I think it's the same as the delta Z in the upper one. The maximum angular distortion, beta in the bottom one, and the tilt also in the bottom one, omega. And there are various structural sensitivity classes 1 to 5, and they are coupled to, in a table, to different structures and type of use. So towers, when they smaller than 24 meters, they fall in SS structural sensitivity class 2, and when they the highest ones fall in 5 and have requirements for the tilting. Then at last, Annex 6. At the end of the drafting of EN 1990, EN 1990 came up with an annex on numerical methods, and it is a bit unfortunate that this should, because all standards already drafted something on numerical methods. We have in Eurocode 7, Part 1, Chapter 8.2. But here comes an informative annex, and Herbert Walter is our representative here. The assumption is that the numerical software should be properly validated and verified, and validation means a comparison with reference solutions, and verification is sensitivity checks for your project. And now then there is a distinction between indirect methods and direct methods. If you put a direct method, then the load and the resistance are following both from the numerical model. If you have an indirect method, then you have the analysis results in a load on a structural element, and the element itself is analyzed, and then from analytical solutions the strength is determined. So the resistance comes from a material model. Recommendations for modeling are given, validation and verification is given. One of the things we were struggling with is that in the annex was another model factor, RD num, introduced, and we had large complaints against it, because these factors make it, you had to derive the model factor for your model, and we argued that the uncertainty in the parameters and in the loads of a geotechnical structure are much greater than often in your model. So we did not agree with that, and so it instead of a recommendation, it became a may clause, an allowance. Well, I think most other things I think is fairly specific. So that was what I wanted to talk about in EN 1990.